the universe we don't see. What if I told you that everything you can see, every star, every planet, every swirling galaxy, makes up less than 5% of the universe? The rest is invisible. A cosmos ruled not by what shines, but by what hides. Two mysteries dominate this unseen universe: dark matter and dark energy. They do not glow, they do not radiate, and yet they control the very fate of the cosmos. Dark matter is the invisible skeleton holding galaxies together, while dark energy is the mysterious force ripping the universe apart. For decades, astronomers have struggled to understand these shadowy forces, and yet with every discovery, the questions only grow deeper. Are we standing on the edge of a revolution in physics, or are we chasing ghosts that will never be caught? The hidden weight of the universe. In the 1930s, astronomer Fritz Zwicky noticed something strange. He studied the Coma Cluster, a collection of galaxies, and realized the galaxies were moving far too fast to be held together by visible matter alone. There had to be something else, an unseen mass exerting gravity. He called it dunkel materie, dark matter. Decades later, astronomer Vera Rubin confirmed the puzzle. By measuring the rotation curves of galaxies, she found that stars at the edges weren't slowing down as expected. Instead, they were moving just as fast as those near the center. According to Newtonian physics, those outer stars should have been flung into the void. Something invisible and massive was holding them in place. Today, scientists believe dark matter makes up about 27% of the universe. Yet we've never seen it, never touched it, never captured a particle of it. Is it a new kind of particle, one that passes straight through us like a ghost? Is it a hidden force we can't yet describe? Or is it proof that our understanding of gravity itself is incomplete? The debate continues, and each possibility threatens to rewrite the laws of physics. The expanding mystery. Dark energy. If dark matter is the glue, dark energy is the great destroyer. In the late 1990s, two independent teams of astronomers studied distant supernovae, exploding stars that serve as cosmic mile markers. They expected to find that the universe's expansion was slowing, pulled back by gravity. Instead, they found the opposite. The expansion was accelerating. It was as if some unseen force was pushing galaxies away from each other faster and faster. That force was named dark energy, and it now accounts for nearly 68% of the universe. Imagine stretching a rubber band. Gravity should make the universe snap back together. Instead, dark energy acts like invisible hands pulling the band further apart. The result: galaxies race away from one another. Stars drift into darkness, and the universe grows colder with time. But what is dark energy? Is it a property of space itself, an energy woven into the very fabric of the cosmos? Or is it evidence of hidden dimensions, fields or forces we cannot yet perceive? Some physicists even suggest it might not exist at all, that instead our understanding of gravity breaks down on cosmic scales. And yet, with every new observation, the mystery only deepens. Hunting the invisible. If dark matter makes up nearly a third of the universe, why can't we see it? Why can't we touch it? For decades, scientists have been chasing shadows. One approach has been to build massive underground detectors, buried deep beneath mountains or mines. These chambers are shielded from cosmic rays and background noise, waiting for the rare chance that a dark matter particle might collide with an atom. Experiments like Xenon 1T in Italy or Lux Zeppelin in the United States have set traps with thousands of liters of liquid xenon, hoping for the faintest flicker of light from an interaction. So far, nothing conclusive. But there are other ways to hunt the invisible. In space, scientists use gravitational lensing, where massive objects bend the path of light. By measuring how light from distant galaxies walks as it passes through clusters, astronomers can map the presence of invisible mass, dark matter halos, surrounding galaxies. These halos act like cosmic scaffolding, shaping the very structure of the universe, and yet the search is frustrating. Every time we think we're close to detecting dark matter particles, whether they are WIMPs, weakly interacting massive particles, axions, or sterile neutrinos, the results vanish like smoke. Each failure pushes us closer to a terrifying possibility. What if dark matter isn't a particle at all? What if it's something far stranger? Galaxies shaped by shadows without dark matter. Galaxies as we know them couldn't exist. Picture a galaxy, billions of stars orbiting a common center. By visible mass alone, galaxies shouldn't hold together. Their stars should scatter like sparks from a fire. But dark matter forms an enormous invisible halo, binding everything in place. This halo doesn't just hold galaxies together. It shapes them. It decides how galaxies form, how they cluster, and even how the large-scale web of the universe looks. Vast filaments of galaxies strung across space like a cosmic spider's web. But here's the twist. Not all galaxies follow the rules. Astronomers have discovered dwarf galaxies that appear to contain little to no dark matter at all. Others seem to have too much. These contradictions baffle scientists and suggest that our picture of dark matter is incomplete. It's as though the cosmos is teasing us, revealing just enough to prove dark matter exists, but never enough to explain it. The dark universe versus physics. The deeper we dive, the more unsettling the questions become. What if dark matter doesn't exist? What if the problem isn't missing matter, but flawed physics? Some scientists argue for modified Newtonian dynamics, MOND, a theory that suggests gravity behaves differently at cosmic scales. Instead of unseen particles, maybe galaxies spin the way they do because our equations are wrong. Others propose bold alternatives. Maybe gravity leaks into extra dimensions, or perhaps unknown quantum effects ripple across space. The debate between dark matter particles and modified gravity is fierce, and the stakes are enormous. If dark matter is real, it could be a portal into physics beyond the standard model, perhaps connecting to supersymmetry or hidden forces of nature. If it's not real, then Einstein's theory of general relativity, the foundation of modern cosmology, may not be the full story. Either way, the mystery is pushing science into uncharted territory. Dark energy and the fate of the universe. If dark matter is the silent sculptor of galaxies, dark energy is the restless force rewriting the universe's destiny. Astronomers now believe dark energy is not a brief phenomenon, but a permanent feature of reality. And if it continues as it does now, the future is chilling. In one scenario, galaxies will drift further apart until their light no longer reaches us. The universe will fade into darkness, a heat death, where stars burn out, black holes evaporate, and even atoms decay into nothingness. But there are other possibilities. What if dark energy grows stronger over time? Then comes the Big Rip, a cataclysm, in which galaxies, stars, planets, and eventually even space-time itself are torn apart. And yet there's also a more hopeful idea. What if dark energy is unstable and might reverse someday? Could the universe collapse back into a fiery big crunch, only to be reborn in a new cycle? These are not just speculations, they're active debates in cosmology. Each theory paints a radically different future for us all. Cosmic what-ifs and unsolved mysteries. Every answer we find about the dark universe leads to even stranger questions. What if dark matter particles could be created in powerful particle accelerators, like the Large Hadron Collider? What if we discover they interact with forces beyond the four we know: gravity, electromagnetism, and the nuclear forces? What if dark energy is tied to quantum vacuum fluctuations, the restless hum of empty space? Could it be the fingerprint of hidden universes pressing against our own? And then there's the boldest possibility of all. What if dark matter and dark energy are connected? Not two separate mysteries, but two sides of the same hidden physics. These aren't just what-ifs, they're questions that could redefine our understanding of reality itself. Humanity's quest in the dark. For now, our tools are still primitive against these cosmic giants, but every new telescope, every new mission brings us closer. The James Webb Space Telescope is already peering into the dawn of time, searching for the first galaxies that may reveal the fingerprints of dark matter. The Euclid mission by the European Space Agency is mapping billions of galaxies to chart how dark energy warps space, and the upcoming Vera Rubin Observatory will scan the night sky with unprecedented depth, perhaps finally uncovering the invisible scaffolding of the cosmos. We stand at the threshold of discovery, but we may also be at the threshold of humility. realizing that the universe is not built for our understanding, that its greatest truths may forever remain out of reach. Conclusion. Shadows that define reality, dark matter and dark energy, are not just scientific puzzles. They are reminders of how little we truly know. Together, they account for 95% of the universe. Everything familiar, stars, planets, people, is just a thin film floating on a vast invisible ocean. Perhaps that is the greatest revelation. The cosmos is not what it seems. Its beauty, its structure, even its destiny is shaped not by light but by shadow. And yet, in chasing those shadows, we discover something profound about ourselves. That curiosity, the drive to seek, to question, to explore, is as infinite as the universe itself. Stay tuned, because in the darkness, the greatest discoveries are yet to come.